This is a U.S. Coast Guard approved radar collision avoidance class, and we're going to start this morning by going over a number of different types of triangles in using radar as a collision device, as an anti-collision device. We use two triangles, the first triangle and the second triangle. Let me first describe to you what each of the triangles do for you. First, with the first triangle, we're going to be able to watch the contact as it appears on the radar scope and follow it. By using a plot, we're going to be able to determine the true course and the true speed of the contact. Now, you'll notice that we do not say target. When you say target, target usually means something that you're aiming for, and we certainly are not aiming for the other vessel. So we're going to call them contacts. We're going to be able to find the true course and the true speed of the contact. We're going to be able to find the relative course and relative speed of the contact, and we're going to have to go into relative directions in just a few moments, because that is one of the most difficult parts of the radar course. We're going to be able to determine what the closest point of approach of the contact is, and from now on we're going to call that the CPA, closest point of approach. We're going to be able to determine how far away the contact is going to pass us, and also the time that it will reach this closest point of approach. To start our course, I want to first put on the board a diagram showing an old method, and this was called the maneuvering board method. It is still in use in some of the military installations. The Coast Guard and the Navy still use the old maneuvering board. However, we have gotten away from it because we have found that the maneuvering board is not as easy to use aboard ship, particularly where you have one man who is both the navigator, the lookout, the radar collision avoidance man. He's doing all these things on the bridge himself, and therefore we have found that the new rapid radar plotting is certainly the better of the two. However, I'm going to first plot on the board a radar scope, and this radar scope is going to represent a 15-mile range. And this is going to be the old maneuvering board system. I do not want you to copy this because it's something that we will not use, but I'm going to put it up here just to give you a start in understanding a little bit about radar plotting. The circle that I have drawn is 15 inches in radius, 15 inches from the center to the outer edge. And I'm going to draw a line which represents our course. Now, the old maneuvering board system, this line that I'm going to draw represents two things. It represents our course, which in this case is north, and it also represents our speed, which in this case is 15 knots. And since we have a distance from the center to the outer edge of 15 inches, we're using 1 inch to the mile, this line then represents two things, our course and our speed. Our course is north, our speed is 15 knots. We pick up a contact on the outer edge of the scope right here, and to make this a little more interesting, we call them up on the radio and ask them, we tell them that we have seen them on our radar scope, and we ask them what their true course and speed is. And the vessel comes back and says, I am making the same speed that you are, 15 knots, and I am steering due west, 270 degrees. So this contact then is heading due west, it is making 15 knots, we're heading due north, and we're making 15 knots. And the question that I ask my class first is, where will this contact appear at the end of 1 hour on our radar scope? Now, you must remember that this radar scope is moving north at a speed of 15 knots. The contact is moving west at a speed of 15 knots. Where do you suppose that contact will be in 1 hour? And at this point, I get all sorts of answers. Some will say here, some will say over on the opposite side, some will say at the bottom. Let's first draw what we call a navigational plot next to this one, and I will show you where we are able to determine just exactly what this contact is doing. I have drawn this line, which represents our course and speed, and I have drawn this line, which represents the contact's true course and speed. If we are at this point at 10 o'clock, we're going to be at this point at 11 o'clock. Now remember, this is a navigational plot and is not a radar plot. If the contact is here at 10 o'clock, it is going to be here at 11 o'clock. So where will the contact be in relation to our position? It's going to be due south of our position, 15 miles, is it not? Therefore, the contact then on the radar scope will appear at the bottom of the scope in 1 hour. Now, how did that contact get there? It had to move along a line which runs in this direction. Now, you'll notice this line is about 45 degrees away from what his true course is. This line is called a relative motion line, and it is the direction along which the contact appears to move on the radar scope. Of course, this is not his true course. This is his relative course. And the length of that line should tell us what relative speed he makes. So I will measure that line, and I get 22 inches, which means that he not only is not moving across the radar scope toward the west, but he is also moving along at a different speed. He is making 22 knots rather than 15 knots. The reason that we have this difference is you can figure it out by using a parallelogram of force. Actually, this is going to be half of a parallelogram of force when we're through. But what we need to do is to figure out what this contact is doing true. We know what he's doing relative, and we know what we're doing true. So we have two sides of a triangle, and by using these two sides, we are going to be able to determine what the contact's true course is. If we took a range and bearing of the contact at 30 minutes, he would be right about here. Now, the strange thing about these plots is that when you take a range, which means the distance off, you take a range and a bearing of this contact, that range and bearing is true. An hour later, if we take a range and bearing of that contact, that point also is true. But when we draw a line between those 2 points, this line is not true. It is relative. And this is where most people make their mistakes, is in not realizing that the picture that you see on a radar scope is not true. It is only relative. The only time that you will see a true picture on radar is if your own vessel is dead in the water. Then certainly everything will appear on its true course and speed. But as long as we are moving, as long as there is any motion to our vessel, what you're going to see on the radar scope is going to be relative. Now, I'm going to show you how easy it is to determine what the true course and speed of this contact is. All we have to do is parallel this line up to the top of our course line and draw that line in, making sure that it is parallel and making sure that it is the same length as the original line, and then close the triangle. The line that I have just drawn represents the contact's true course and speed, and I think you can see that. Certainly the contact's true course is to the west, and certainly this length is 15 inches, which represents 15 miles, 15 knots. So all we have done then in this plot is paralleled the contact's relative motion up to the top of our true course, drawn it in to figure out what the true course and speed of the contact is. Now you must remember that to get any one line, you must know two others. We knew this line, which was our true course and speed. We knew this line, which was the contact's relative course and speed, to get the third side. And in this plot, now we have determined what the true course and speed of the contact is. Now let's go just a little bit farther. Supposing we have a buoy. And of course, the buoy is dead in the water, and the buoy is right here at 10 o'clock. Where do you suppose that buoy will be at 11 o'clock? It's dead in the water. However, it will be right here at 11 o'clock. Now that means that the contact has moved from this point to this point in 1 hour. Does a buoy have a course? It has a relative course. What is the relative course? The relative course is going to be south. Does it have a relative speed? It does. What is the relative speed going to be? From here to here is 15 inches, 15 miles. That means that the relative speed is 15 knots. And right here, I would like to make a point because it is important. Whenever you pick up a contact that is on an opposite but parallel course to yours, making the same relative speed as your true speed, that contact is dead in the water. And this will take place anytime you see that. But here is a contact dead in the water that has not only a course, but also a speed, relative. Supposing we pick up a contact right here, and an hour later it's right here. What do you suppose that contact is doing? First, let's figure out what the relative course is. The relative course is south, just the same as the buoy was. How about the relative speed? The relative speed would be measured between these 2 points. What do you suppose that contact is doing? The strange thing is that contact is steering the same course that we are, north, but it is moving slower than we are. Therefore, it appears relatively to be heading south. However, its true course is north. Let's try one more. Supposing we take and put a contact here, and in 1 hour, that contact is still there. What do you suppose he's doing? That contact is moving at the same course and speed as we are. And what I would like you to get in the habit of doing as you work these plots is always try to visualize what you're looking at when you plot. Don't just draw a lot of lines and try to understand what those lines are. Try to visualize it. Remember, we are always in the center of the scope, and we never leave the center of the scope for any reason. I might change that a little bit. I should say in the center of the sweep, but in most cases the center of the sweep would be the center of the scope. We are always in the center of the scope. We never leave the center. And try always to visualize what you see here, such as this contact which is moving slowly toward us. If you were standing on the bridge looking out and you saw a vessel up ahead of you and you couldn't determine just which way he was going, and you watched him for an hour and he got closer, you would certainly know what he was doing just by looking at him. So I'd like you to always get in the habit of trying to visualize what you see on your radar scope or when you're plotting on paper. Now, most of the plotting that we're going to be doing will be on paper, and it will be done on a radar transfer plotting sheet. It gets its name from the fact that we are transferring information from the radar scope to a plotting sheet. Now, why would we do this? Why wouldn't we plot directly on the face of the scope? The reason is that unless you have a reflection plotter, and we're going to be talking much more about that a little bit later, unless you have a reflection plotter, you cannot plot on the face of the scope because of parallax. And as I said, we will talk a little bit more about that as we go along. Therefore, most of the plotting that we do will be taken, the information will be taken from the radar scope, and it will be placed on a radar transfer plotting sheet. You will do most of your plotting on paper. I would like to continue now by drawing a plot from our books, and we are going to be going over a good many of our plots on the board so that you'll be able to see what they are. And I want to call your attention to one thing. When I make a diagram on the board, remember that I have no degrees. It's very difficult for me to get the exact direction. Measurements are also difficult, so my plot may not look exactly the same as yours. I would like to go over the radar transfer plotting sheet that we have given you and cover a few of the parts that you have on the plotting sheet so that you will understand it a little better before we start plotting. Now you'll notice with the radar transfer plotting sheet that on the left side of the sheet there are 4 range scales. You have the 6, 12, 3, and 24 mile range scales. You will have to decide before you start plotting which of these 4 scales you're going to use. How will you determine this? Well, you will have to decide first by looking at your problem to see how far off the contact is when you first pick it up. If the contact is between, say, 6 and 12 miles, you will certainly want to use the 12-mile scale, which is the scale. And I would suggest that when you decide which scale you're going to use, that you circle the top number. As in this case, you would circle the 12. If it were the 6-mile scale, you would circle the 6. You'll notice the numbers, the large numbers that appear under 12, the 2, 4, 6, 8, 10, and 12, they represent the distance between the rings. In other words, the first ring is 2 miles, 4 miles, 6 miles, and so forth. So all of the large numbers represent the distance of the rings. On the 6-mile scale, you'll notice 1, 2, 3, 4, 5, and 6. Each of the rings are 1 mile. Each of the rings are 1 mile apart. With the 24-mile scale, again, you'll see some large numbers, and they will indicate which of the rings, the distance between each of the rings. So again, be sure that you indicate which scale you're going to use, and we'll talk a little bit more about which scale you are going to use. Remember also that when you plot, you will always try to get the contact as far away from the center as you possibly can. In this way, you will have a much larger plot to deal with and a much more accurate plot. You'll notice in the 4 corners of the sheet, there are spaces for time, bearing, and distance. And these will be used in case you have more than one contact. You will be able to put in these squares the time, bearing, and distance each time that you pick up the contact. The little round circles can be used to designate the contacts A, B, C, and D. Let's go over to the right side. You'll notice that there is a logarithmic time, speed, and distance scale here. I'm going to show you how this is used as we get into our first plot. And you can use this in place of a calculator or any other method that you might have been using for finding your time, speed, and distances. This space you may use for any computations that you may want to make. I would like you to take your radar observer manual and turn to page 80, if you will, please. And you will find on page 80 the plots will commence. Now there are a total of some 25 different plots that I would like you to try to work out between now and the end of the course. We're going to start first with a plot that has to do only with the first triangle, and that will be plot number 7-4. I would like you to do something for me. Each of the sheets that you work on, I would like you to place your name, today's date, or the date on which you are working, and the problem number on each sheet. Now you'll notice that you can work on both sides of these sheets. Therefore, I want your name, date, and problem number on both sides of the sheet as you work. So if you will, again, turn to page 80, and we're going to work together problem 7-4. Now I already have drawn a circle representing the same thing that you have on your plotting sheet. Remember again, as I explained to you, that my diagram may not appear exactly the same as yours does because you have your degrees and so forth that I do not have on the board. You notice that I have placed the number 7-4 up on the top, and we're going to start by drawing some of the lines that are necessary in the problem. Let me read the problem first. It says, our own ship is on a course of 0, 0, 0 degrees true. Now, I want to call your attention to one other thing that you will notice as we make our diagrams and our plots. You will notice that I use different types of lines, different indications of points, and the reason for this is so that you can look at the plot and immediately decide what each of the lines are by its description. Now I would like you to start, and I'm going to go through this rather hurriedly. I do not expect that you're going to be able to follow me all the way through because I will make this diagram rather quickly, but try to keep up with me as best you can. Please do not draw any lines that you don't see me draw up here on the board, and please make sure that you draw all of the lines that I draw. Going back to the problem again, it says our ship is on a course of 0, 0, 0 degrees true, and that's the first thing we're going to do. We're going to draw a diagram, we're going to draw a line representing our course. This is going to be a dotted line. The reason it's a dotted line is so that it will distinguish it from all the rest of the lines that you will draw. That line represents our course, and it represents our course only. If you'll remember back a few minutes ago with the maneuvering board problem that I had on the board, there the length of the line was important. In this type of plot, the length of this line does not mean anything. The length of the line does not mean that that is our speed. It is only the direction that we are interested in, and the direction in this case is north. It goes on to say our speed is 12 knots, and we're not interested in that yet. At the time shown below, a radar contact was observed in the following bearings and at the listed ranges. And then it says at 4:10, the contact was bearing 035 degrees, 11.1 miles. So what I'd like you to do, first, we've got to decide, before we can start plotting, is what scale we're going to use. And since we are picking up the contact at 11.1 miles, certainly we are going to use the 12-mile scale. So up here, I want you to circle the 12, representing the 12-mile scale, so that you will remember always to go back to that scale. Don't go to the wrong scale, because if you do, you certainly will not get the correct answer. The next thing to do then is to plot that contact. The first time we pick it up is at 4:10, bearing 35 degrees, 11.1 miles away. And I want you to draw that point. Use your triangle, lay it off on 35 degrees, and use your dividers. Measure 11.1 miles on your scale, on your 12-mile scale, and plot that contact. It should look something like that. Besides making the plot as we have here, I want you to use a letter. We are going to use 3 letters in all of our plots, and these letters will help us to remember what each of the lines represents. In this case, we are going to use a small written letter R, a small written letter R, not a capital, but a small written letter R. This letter is going to be part of our 3-letter scheme that will enable you to determine exactly what each of the lines are. Now, I think you'll remember that when we used the maneuvering board, we had an hourly plot. In this case, we are going to have plots that are much smaller, and they are not going to take place in the center such as we had with the maneuvering board. And since this is called a rapid radar plot, we are going to start plotting immediately. As soon as we pick up the contact the first time, we are going to start our plot. And we do this by paralleling this line over to point R. And I'm going to do that, and then I'm going to explain to you how to do that with your triangles. That line should be about 2 inches long. If you have never used triangles to parallel lines, and I don't believe that you're going to be able to see these triangles very well, but your instructor in the classroom will show you how to use your triangles to parallel lines. We recommend that you use triangles rather than parallel rulers for accuracy. And you'll see what I mean as you get farther and farther into the course. The way this line can be paralleled is by laying the long edge of one triangle on the line that you wish to parallel, and laying the long edge of the second triangle along one of the short edges of the first triangle, and moving the triangle in either direction until it parallels the line over to where we have this line drawn. We have not discussed the speed of our contact yet, rather the speed of our vessel yet, other than describing that it is 12 knots. Now we are going to indicate on this line, and remember that this line represents our course. We're going to make marks on this line to indicate our speed. And in this case, our speed is 12 knots. We are going to use 6-minute increments along that line. And if we are making 12 knots, it means we are going 12 miles in 60 minutes. How far will we go in 6 minutes? All we have to do is move the decimal point one place, and we get 1.2 miles in 6 minutes. So if we are going to move 1.2 miles in 6 minutes, I want you to take your dividers, go over to the 12-mile scale, measure 1.2 miles, come back, and make a mark 1.2 miles from point R. Once you've done that, then I want you to make another mark 1.2 miles from the first mark you made. Now these marks, as you notice, are not just marks, but they're lines. And the reason for this, again, is to distinguish them from other markings that we have. What this means then, if we are going to make a 6-minute plot, we're going to use the first point. If we're going to make a 12-minute plot, we're going to use the second point. And we'll get into that a little more fully as we go along. Now you'll notice that we paralleled this line over, and we drew it down. Remember that our ship is going to the north, is heading to the north. If you wish to help you remember that, you may want to put a little arrowhead right here in this first plot, just so that you will remember it. Now, remember again, we have paralleled this line over, and the reason that we have drawn it from point R is we don't know where it's going to begin yet. We do know where it's going to end. It's going to end at point R. So remember that it must always go in the direction of our course toward point R. Now we're going to continue with our plot, and our next plot is at 4:16, 9.2 miles away. So I want you to make that plot next using your dividers and your scale. This plot will be labeled only with the time, no letters. Just 0416 and the plot. Now we are going to pick up the contact the third time, and this is going to be at 4:22, and it is going to bear, it is going to be 7.3 miles away, and it's going to bear 25 degrees. The last one was 31 degrees. This one will be 25 degrees. This point will be labeled not only with the time, but also with the letter M, a small written letter M. So we now have two letters. We have one letter R, and we have one letter M. And these letters have only been on marks that we have made where the contact is at that particular moment. Now I would like you to draw a line through all three of these points and draw it beyond the center, starting at point R, drawing it through point M, and continuing past the center. That line is called the relative motion line, and I would suggest that for this first plot you place the letters RML, relative motion line. The next step is going to be to determine which of these 2 points you're going to use. Since this is a 12-minute distance between point R and point M, this also has got to be a 12-minute distance, and so this point here is going to be E. Now we are going to draw a line from E to M, and that will close our triangle. Quite similar to what we did a little while ago with the maneuvering board. Now we have arrived at a point where we can start answering some of the questions that are in the book. And the first question asks you, what is the distance which the contact will cross dead ahead of our own ship? And this is what I explained to you a little while ago. I want you to try to understand what you're seeing and try to visualize it. Remember, we are in the center of the scope. We are watching this contact move along this line. When it is dead ahead of us, where will it be? It's going to be right here. And this is going to be called the crossing distance. And to determine how far away the contact is at that point, all we have to do is measure that distance, go up to the scale, the 12-mile scale, measure it, and the answer should be 4.3 miles. 4.3 miles. So I'm going to put that over here. 4.3 miles. That is the distance from the center to the crossing distance. 4.3 miles. So as that contact is moving along, we know that when it's dead ahead of us, if we look out, we're standing on the wing of the bridge and we look out and see that vessel, it is going to be 4.3 miles away at that particular moment. All right, the next question. They want to know what the relative course is and the relative speed. All right, now to find the relative course, and this is something that they don't usually ask, but you'll see, since this is the first plot that we're making, they ask a number of questions that probably will not be asked again, just so that you will be able to understand the plot a little bit easier. They want to know what the relative course is. Now, the relative direction. To find that, we must parallel this line down to the center. And remember that the radar plotting sheet is the same thing as what you would have on a chart. If you were laying off a course on a chart, you would have to bring that course down to a compass rose to get the true course. You must do the same thing here. The only difference is that the compass rose here is the entire radar plotting sheet from the center to the outer edge. Remember that whenever you want to get a course, you must bring that course down to the center. And in this case, you would bring this relative motion line down to the center and get a course that would be down here somewhere. The true course would be 234 degrees. 234 degrees. Now, they're asking for something else as well. What is the direction of relative motion and the speed of relative motion? Now, how are we going to find the speed? And I'm sure that aboard ship or aboard your boat that you have found speed by running between two buoys, by running between any distance, any known distance, and noting what the time is. You should be able to determine what the speed is. So in this case, we're going to measure the distance, using your dividers, measure the distance between 410 and 422. Take that measurement that you have in your dividers, go over to the scale, the 12-mile scale, and you will see that it is 4 miles. Now, to show you how easy it is to use these 6-minute increments, which we're going to be working with, we said 4 miles. 4 miles in how many minutes? 410 to 422 is 12 minutes. So it's going to be 4 miles in 12 minutes. If it's 4 miles in 12 minutes, how many miles will it be in 6 minutes? It's going to be half of that. It's going to be 2.0 miles in 6 minutes. What will it be in 60 minutes? It'll be 20 miles in 60 minutes. So what will the speed be? The relative speed is going to be 20 knots. And I would suggest that you make a mark here, relative speed 20 knots, so that you'll have it. And also in your answers, 20 knots. Now, by the way, you should be putting all of these answers that you get, not necessarily what I get, but what you get in your book. This book is yours to keep, and I would suggest that you put the answers in the places where they are supposed to be in this book. So we have just finished with B, and we had 234 degrees for the direction of relative motion, which we parallel down to the center, and I would also suggest that you make a little mark on the outer edge of the scope when you do that. You have found that, and now you have also found that the relative speed is 20 knots. Remember, this is relative. This is not true. There are so many people that get the idea that when you look into a radar scope, everything you see is true. That is not the case at all. And as you can see here, this is relevant. This is the direction that that contact is going to move. It is not moving. It is not moving as if the ship were moving along the line like this. It is moving on a different course, which I'm going to show you in just a few minutes. All right, let's go to the next answer. What is the true bearing and distance of the CPA, closest point of approach, from our own ship? Now we must determine how close that vessel is going to get to our vessel. And you might think, well, he's crossing our bow here. This must be the closest point of approach. It isn't, because when you get down in here, it's going to be a lot closer. Now, how do you determine the closest point of approach? It is always done using a triangle with a right angle, and always, and I don't know whether you're going to be able to see this or not, but always lay one edge, one of the short edges of your triangle along the relative motion line, and the other short edge should touch the center of our vessel, or the center of the scope, I should say, which is this point. And that should give us a closest point of approach. Remember, it must be a right angle. And it should be labeled closest point of approach. The closest point of approach means the closest that that contact vessel is going to come to our vessel. So the closest point of approach then is measured by taking your dividers and measuring the distance from the center to that point. And in this case, the closest point of approach should be 3.5 miles. 3.5 miles. And I'll put that on our answers over here. 3.5 miles. Also, I would suggest that when you find the closest point of approach, that you draw a line showing the direction of the closest point of approach. Because the next question is, what is the bearing of the closest point of approach? And you must extend that out to the outer edge, make a mark, bearing of the CPA, and the bearing of the closest point of approach in this problem is 324 degrees. Now, I want to mention one other thing here that may be a little confusing. Just because this particular triangle is a right triangle does not mean that all of the triangles that you're going to construct in working your plots will be right angles. They will not. It just happens that every now and then we will come up with a right triangle. In this case, we do have one. We will not necessarily have one in all of the problems that we work. One other thing I'd like to call your attention to is that everything that we are going to be doing in these plots will be true. Whatever our course line is, if our course is 30 degrees, it will be the heading flasher. This line that we have drawn here, the dotted line, will be in the direction of 30 degrees. Remember, everything is true. This is called a stabilized presentation. And what that means is that if we should change our course, the only thing that moves is the heading flasher. It will take up a new position. It is called a stabilized picture because the plot will remain fixed. The contact will not move out of its position when we change the course. Most of the vessels that we have in use today are using an unstabilized picture where the heading flasher always points to the top of the scope. And we're going to be talking about that quite a bit as we go on. But for now, remember, everything that we will do in this plot will be true with, of course, the exception of the relative motion line. All right, let's go on. We have gotten the true bearing and distance of the closest point of approach. Now, D says, what is the distance to go from the 422, which is the last plotted position of the radar contact, to the closest point of approach? What they want to know now is the distance from here to the closest point of approach. So I want you to measure that distance, go over to your scale, and see what it is. It should be 6.5 miles. The reason that they have asked for this distance is because they want to find out something else. You already know what speed the contact is making relatively. Now you have a distance, and they're going to want to know the time of the closest point of approach. And I believe that's the next question. E says, what should be the time of the CPA? They want to know. They know that it's 4:22 here. What time is it going to be here? And I think you have run into this situation many times before, where you have passed a lighthouse and you want to try to figure out what time you're going to get to the next buoy or the next lighthouse or the next point of land. How would you figure it out? You know what your speed is. You know what the distance is. It is just a simple matter now of using your time, speed, and distance scale or stepping it off. Since we have not learned yet how the logarithmic time, speed, and distance scale works, let's just step it off. And the way we would do that is take the distance between 4:16 and 4:22 and walk it down until you get to the closest point of approach. This is not the most accurate way of doing it, but it is the simplest and quickest way of figuring out the time of the closest point of approach. If you have done it correctly, you will find that the time is 4:41. Before we're through, we're going to discuss the use of the logarithmic time, speed, and distance scale, and I'll show you how that works. It is one of the most accurate methods of finding time, speed, and distances that we're going to be working with throughout our plots. The F, what is the distance our own ship travels in the time frame between 0410 and 0422 plots? In other words, they want to know how far have we moved in this distance. And we have already done that. You remember that that our speed in this problem was 12 knots, and so we made this 1.2 miles and another 1.2 miles, a total of 2.4 miles. So the answer to that question we already done, and it should be 2.4 miles, 1.2 and 1.2, 2.4 miles. Next, G, what is the true course of the contact? The true course of the contact is going to be this direction, E to M. And I think this might be a good time to discuss the letters that we have up here so that you will remember what they are and what each of the sets of letters mean. In other words, in this case, E to R. Isn't E to R the same as the direction of our course? So E to R, R course. E to R, R course. R to M, that's easy. R to M, relative motion. The last one, E to M. E to M, them, their true course and speed. So there we have it. E to R, R course and speed. R to M, relative motion, the relative course and speed of the contact. And E to M, them, which means the contact's true course and true speed. So now they're asking for the true course of the contact. If you will parallel this line down to the center and draw it out, not draw it out, but mark it out, you will find that it should be 270 degrees. True course of the contact, 270 degrees. The next question, H, what distance, if any, was run by the contact in the time frame 410 to 422? Now you notice they did not say relative. They said, what is the distance run by the contact? The distance run by the contact is measured from E to M. Just like each of these lines that you have in this triangle are all distances that have been run in 12 minutes, so will this distance be the distance that's run in 12 minutes. So I want you to measure that distance, E to M, and see what you get. And it should be 3.2 miles. If you have gotten 3.2 miles, and remember, as I told you before, you should be putting these answers in your book. The last question says, what was the speed of the contact if underway and with way on it? Well, of course we know it's underway, and we certainly know that it has a true course of 270 degrees. So we know that it's moving. Now we want to know how fast it's moving. If the contact has moved 3.2 miles, 3.2 miles in 12 minutes, how far will it go in 6 minutes? 1.6 miles in 6 minutes. What will it do in 60 minutes? 16 miles in 60 minutes. So what is the speed of the contact? True speed, 16 knots. We have finally completed one plot, and remember that this is the first triangle only. And what have we discovered? Well, first, we know the direction of relative motion. We know how fast the contact is moving along that line. We know the closest point of approach, how far away from us that contact will be at the closest point. We have found the time of the closest point of approach. We have found out how far away from us the contact is when it crosses our bow. We have found the true course and the true speed of the contact. We have done all that with what is known as the first triangle. We are going to continue, not with this problem, but with another problem a little bit later, which will go into the second triangle. And with the second triangle, we're going to be able to determine if the contact is coming in on a collision course or nearly so, what we can do to get out of its way. Should we change the course? Should we change the speed? Should we do both? What happens if there's more than one contact? And we're going to be able to do all this by using the second triangle. So for this, we have completed all that we're going to do with the first triangle, and our next presentation will be the second triangle. We're going to discuss next the logarithmic time, speed, and distance scale, which is found on your radar transfer plotting sheet. And I would like you to turn your sheet sideways so that you can read logarithmic time, speed, and distance scale with the white space up at the top. And take a look at it. You'll notice that the numbers start on the right-hand edge and with 60, and they go all the way down to a 0.1. You're not able to see that on your screen, but the numbers will range from 60 minutes all the way down to 1/10 of a minute, which is all the way over to the left. Now these numbers are not only minutes, but they're also distances, 60 miles, 40 miles, 30 miles, whatever you might have. There are two rules that you must use in learning how to use the logarithmic time, speed, and distance scale. The first rule is that whenever speed is given, you must always set your dividers up on speed. For example, if your speed was 20 knots, you would put the right leg on 60, the left leg on 20. Now you would have your dividers set in such a way that they represented 20 knots. No matter where you move along this line, the right leg will be time, the left leg will be distance. And this is the second rule. Right leg is always time, left leg is always distance. And you can remember that because you'll notice that all the way to the right is 60, and there are 60 minutes in an hour. So remember that you will always have to go back to the 60 if you're dealing with speed. So here we're set up with 60 minutes and 20 miles, which means the vessel is making 20 knots. So if I want to know how far this vessel goes in 30 minutes, and you know it's going to be 10, I'll put the right leg on 30, the left leg will show 10. If I want to know how far this vessel will go in 15 minutes, put the right leg on 15, the left leg will show 5. Now let's go the other way. Let's work out a problem to find the speed. Supposing we have a vessel that makes 4 miles in 8 minutes. What is the speed? So I set the left leg on 4, the right leg on 8, and then pick them up and bring it down to 60. The speed is 30 knots. So let's do another one. Supposing we have a vessel that goes 5 miles in 12 minutes. What is the speed? I've set it up 5 miles to the left, 12 minutes to the right. Bring it down to 60, 25 knots. Now let's look at the problem that we have on the board here and see what we can do with it. You remember this problem? 7/6. This was our relative speed. So if we measure the distance between R and M, this distance, and remember that you cannot take this measurement and go over to the logarithmic time, speed, and distance scale. You can only bring numbers to that scale. So if we measure this distance, go up to our distance scale, our 12-mile scale, and measure that, you will find that it is 2.4 miles. That means 2.4 miles in 12 minutes. I'm going to come over to this scale, 2.4 miles in 12 minutes, and I want to know what the speed is. 12 knots. And you remember that was what the relative speed was in this problem. Let's take the new relative speed, and that was from R1 to M. And we'll measure this distance. Take this distance, go to your 12-mile scale, and you'll find that that distance is 4.4 miles. Coming back to our logarithmic scale, 4.4 miles in 12 minutes. Pick it up, go down to 60, and we find 22 knots. And you remember that is the new relative speed. Once you have your divider set on a speed, no matter where you go along this scale, the right leg will always be time, the left leg will always be distance. If you will turn in your book to page 64, there are 18 problems that I would like you to do sometime when you get the chance. The first six give distance and time to find speed. The next 6 give distance and speed to find time, and the last 6 give you time and speed to find distance. The answers are directly below it, and at the bottom of the page is a note and a diagram showing you how to use this scale.